everyone. We are going to talk about the radar transfer plotting sheet. Be sure that you have two triangles, a good sharp pencil, and dividers with a sharp lead. Make sure with your dividers too, your points are of equal length. So with this example, we're going to start right off with our ship's course and speed. We have a course of 000, a speed of 24 knots. We could write this information down on the bottom right corner of our radar transfer plotting sheet. We'll need this information in the future, so we don't want to lose track of it. Always get in the good habit of writing it down. Okay, so on your radar, let's say that you detect a target. We'll call him target 1. Now you can record any of this target's information in any of the 4 corner boxes. But for me, I'm going to choose the top right, label in that little circle, number 1 for target number 1, write the time it was taken at 0000, his bearing of 040 degrees true, and his distance of 10 nautical miles. Now we have to choose our range scale. The best range scale is always one that will fit all of the information, but at the kind of closest range so that you get a big triangle. I'll see what I'm talking about later. So I'm going to choose the 12 nautical mile distance scale since our target is only 10 nautical miles away from us. So before even plotting our range, first we want to plot our bearing. Using the center hash mark of our radar transfer plotting sheet lined up with the bearing 040, making sure it's perfectly lined up, we can draw that little hash mark. And now I kind of know the area I want to draw that hash mark, because if we're in a 12 nautical mile range scale and he is 10 nautical miles away from us, he should be on that 5th ring away from us. If you just count out 2, 4, 6, 8, 10, he is perfectly on that 5th ring out. Now for demonstration purposes, I am going to make everything in Sharpie so that it is much easier to see on the screen. You see me being very exact right here. Okay, so we have our first range and bearing plotted. We wait 6 minutes. We take another range and bearing at 0006. His bearing is 037 degrees true, and his distance is 7 nautical miles away from us. So we do the same thing. We line up our triangle on 037, making sure it's perfectly in line with that center hash mark and our 037 on the outside of our radar transfer plotting sheet. Now we don't know exactly where 7 nautical miles is. We know it's somewhere between 6 and 8 on those range rings. So I just draw a line, decently long enough in the middle to kind of guesstimate where 7 nautical miles is, and then I go in with my exact measurement from the center. Now again, I'm just going to go over in Sharpie, trying to be as exact as possible just to show you how this will show up on your page a little bit more distinctly. I highly, highly recommend using a very small lead pencil to make all of these measurements very exact. So we have our R and our M. Our R was the first point we plotted. Our M is the second. You can see how they're moving relatively towards us. This is 6 minutes apart. They are moving close to us, almost with the same bearing. If we connect our R and our M, we are able to see the future prediction of where they will be moving relatively to us. We call this red line the relative motion line, or RML for short. Now again, this is how they will be moving relatively to us. Right here is where they will be moving the closest to us relatively. We can call that our CPA. A way that you can measure that distance exactly is by creating a right angle on your triangle and to your center hash line. Make sure that your right angle is perfectly lined up before you draw your little hash so that it is as accurate as possible. Again, this is our CPA, our closest point of approach with this vessel. Now we can do a few things with all of this information already. We can measure from the middle to that CPA how close they will get, which looks about 1 nautical mile. Now again, I'm using Sharpie, but you should be able to, with pencil, get into closer decimals. Put that CPA, 1 nautical mile. Where can I put that information? I put it right where it says CPA on that top right corner of information. Now I could also see a relationship between R and M and R to the CPA. Now if it takes 6 minutes for this travel to relatively move from R to M, we will eventually be able to calculate how quick they will get to their closest point of approach as well. The way we calculate this is with 60 D Street. This is the main formula of all of radar plotting. D stands for distance, the S stands for speed, and the T stands for time. We multiply the distance by 60 if we are working in minutes. If we are working in hours, we just drop that 60. So we are able to measure the distance from R to M with the time it took, which is 6 minutes. From R to M took 6 minutes. That's where we put our T. For distance, we measure and get that exact number of 3 nautical miles from R to M, again, for 6 minutes. So 60 times 3, and then divided by 6, gives us our speed that they are traveling along this relative motion line. This is their relative motion speed. So relatively to us, they are going 30 knots. They are moving 30 knots along that relative motion line. So all of their relative motion is measured from R to M. That's why we label them R and M, to make it a little bit easier. Once we have their speed, we can also find out how soon, again, that they will be traveling along that line to get to their CPA, their closest point of approach. Notice where I wrote relative motion speed as well. There's not necessarily a spot for it in these corner information centers, but it's a good place to keep this information so that we don't lose it. This will come in handy once we try to find our TCPA, which is our time of CPA. Between that R and M, we can also find our relative course information. We just simply measure that RML in the direction of R to M. So we line our triangles up along that line, and then we drag it to the center. Make sure that your triangle doesn't slip like it just did right there for me. But you measure it along, you drag it down to the center, and notice how I'm using the actual line on the triangle for measuring instead of the edge. The edge can sometimes slip or not give as detailed accuracy. So my relative course, I measured 2 to 6 degrees true. And again, there's no spot to specifically put that, so I just write it down at the bottom. I have my RMS for relative motion speed and my RMC for relative motion course. Now that I have that information, again, r to m equals your relative motion of that target. Now with all that information, I could find their TCPA, or how soon they will get from R to my CPA along that line. This distance right here is what I'm going to measure with my dividers and use their relative motion speed to calculate with 60 D straight. Again, from R to your CPA. So I'm measuring right here, trying to be very exact. And I find that my distance is 9.9. So again, we are doing 60 D Street. Because we're working in minutes, D, which will be our distance of 9.9, speed, which is their relative motion speed because they're traveling along that relative motion line of 30 knots, and then X for time. So again, 60 times 9.9 and then divided by 30 should give us our time of CPA, or TCPA. So we get 19.8. Now that 19.8 is in minutes. We need to add that 19.8 to the time of our R. So if we started at midnight at 0000, we just add that 0000 to 19.8 minutes to get our time of CPA. We could write that in that top box area just below that CPA. And make sure you write the decimal. The decimal is pretty important for your radar transfer plotting sheet for Coast Guard questions. So we want to have that high level of accuracy. Okay, now we have all the info that we can get already. Now let's take into account our speed and our course. So if we take our heading of 0000, sorry, just 000, there's no 4 zeros. We take our heading, we slide it over, and again, make sure that you don't have any slippage, you're very accurate. I had some slippage and I started over. I'm not rushing through this. We slide it over to our R. Now we are going to draw our heading line, or rather the reciprocal of our heading line from R. Now straight down, that was 000, so that line from R should be going in the direction of 180 degrees. Now to take our speed into consideration, we were going 24 knots. We have to figure out where we're supposed to measure from R. So we're trying to find our distance. Our speed is 24 knots, and our time, we're doing a 6-minute interval plot, so we will multiply 24 by 6. And if you notice, whenever I'm doing these 6 minutes, it's really just moving over a decimal place. So I am going to get a distance of 2.4 nautical miles. That is where, or rather how far, I should plot from R to create E. Now, when I say E, it's just another way of labeling something. A phrase we like to use is we are E to R. So we're essentially mimicking our own motion onto this target to be able to find some more information about them. So we label that point, that distance of 2.4, we label it E at 0006. Be sure to always timestamp everything. And again, we call E to R, we are, because that is the mimic of our own ship's motion on another target. Now with our information actually plotted on this target, we can connect E to M. For any true motion, we are measuring this E to M line. Another phrase we like to use, E to M is them. We are able to find the E to M distance and bearing for our true motion speed and our true course of that vessel. So let's start with their true speed. We just measure from our E to our M. In our triangle, we look at that measurement, again trying to be as exact as possible. And we find that measurement using our 60Z street. Our distance was 2.2 nautical miles. Again, you might get something slightly different if you are using a pencil. That is okay. 60 times that distance of 2.2 equals speed. Well, we're looking for speed. And time. Now that's a 6-minute triangle that we're using. So multiply by 6. So 60 times 2.2 divided by 6. I'm going to take a crazy guess and say it's 22 knots. Again, we call this the tense rule if we're doing 6 minutes of plotting. We can just move over our distance decimal, if you notice that. So their true speed, their E to M, their true speed is 22 knots. We can write that down on that top right corner. And now let's get their true course. So for true course, just measure the angle of E to M line. Be sure to be going in the direction of E to M. And then you move it into the center. Double check again that you are going in that correct direction. E to M is them. Have sturdy hands and move that triangle to the center. Follow that line on that triangle to get a very exact measurement. Again, you can see I bumped it, but my hand holding the other triangle was sturdy and moved it back to get that exact measurement. So I got a course of 278 for their true course. Again, we can record this in the top left corner where it says other ship course, 278 degrees true. Now there's a few other things that we can see with this plot. We have all the information that we filled out on the actual plotting sheet, but we're able to tell now from their true course what direction they were actually going, so we can figure out what rules of the road situation that we belong into. Now before we get there, again, I'm just going to annotate E to M is your true course and your true speed information. E to M is them. R to M is that relative motion, how they are moving relative to us, how close they're going to get to us. We're able to find their CPA and TCPA from their R to M information, their relative motion. And again, E to R, we are ER. That is our ship mimicked onto their triangle. Okay, so back to E to M. Knowing their true course, we can figure out which way they actually are supposed to be heading. We could draw a little ship right there. So they are actually going, again, that heading of 278. I just like to draw a little picture of it. They're moving along the relative motion line, but they are facing the way of E to M. So we're able to figure out our rules of the road. Are we stand on? Are we give way? Is this a crossing, head-on, or overtaking situation? I always like to draw a ship with both side lights on it. When you look at the aspect of a ship, If you see a red side light, red means stop. If we are physically looking at that red side light, red means stop, and we are the give way vessel. Now, for some reason that, this ship was actually going on a heading of 090, and he was bearing around 310 from us, and we saw his green side light, we would then be stand on. But again, in this exercise, we are give way. I hope this exercise was helpful for everyone. Please let me know if you would like more to see. Thank you.